Well, hello there, chemistry fans. We're here with our first video for Chapter 5. We're going to be talking about ions. So, first thing to get going, quick review. We've been learning about atomic structure. We know about protons and neutrons and nucleus, electrons going around the outside. And so electrons are an important part when we talk about chemical reactions. It's all about this exchanging of electrons, giving, taking, or even sharing of electrons. So changing the nucleus is a nuclear reaction. That is not a chemical reaction. Chemical reactions are all about the electrons. So good thing we know, good foundation already. Next thing we need to talk about, though, are valence electrons. And valence electrons are the electrons in the outer shell. They're so special, they get their own name. So the reason we have a special name for them, this is where all the action happens. If something's going to lose electrons, it's going to lose it from the outer shell, the valence electrons. If it's going to gain electrons, it's going to gain electrons into the outer shell. So that's where everything happens, and that's a key thing that we need to know about. A great way to figure out what's going to go on is using the octet rule. And the octet rule should make you think about 8, octagon, and all those things going along with that. So when we think about our noble gases, and most of them have 8 valence electrons, except for helium, right? Helium's kind of weird. It's got that tiny little shell with only 2 in it. But besides that, all the noble gases have 8 valence electrons. So that is a very stable configuration. Having the S and P subshells that are filled is going to be very stable and non-reactive, right? They don't actually have filled outer shells, except for neon and helium, but everything else just has 8, and it's super stable that way. So the octet rule, here's a good thing to know, that most elements take the easiest way to get 8 electrons in their outer shell. So trying to be like a noble gas, that's another way of thinking about this. And so another way I like to think of it is that the elements try to be like the nearest noble gas to them. And that may be above them in atomic number, or maybe below them in atomic number. So as we think about some exceptions of this, well, the octet rule, pretty obvious exception is helium. Helium, we know, only has 2 valence electrons, but it's a noble gas and it's very stable. But it doesn't follow the octet rule. Another exception of that would be hydrogen. Hydrogen would like to be like helium, so it would want to gain 1 electron to have that filled shell like helium. But again, it's only 2. It's not following the 8 rule. So can you think of another exception? Well, think of the other side of helium. If we talk about lithium, and lithium here has 2 in the first and 1 in the second. And the easiest way for it to be like a noble gas would be to lose that 1. So lithium has 2 in the first, 1 in the second. So by losing this 1, it then has a configuration like neon. Well, can you think of another one? Well, beryllium, that's also an exception there. It's got 2 in the first and 2 in the second. To gain electrons, it would have to gain 6 electrons to be like neon, but it only has to lose 2 to be like helium. So we also have that for boron, and then carbon sometimes will fit that bill there too. So as we think of elements like chlorine, chlorine here is a good one to talk about. And chlorine has 2 in the first shell, 8 in the second shell, and 7. So we think of gaining or losing electrons to be like a noble gas. Well, chlorine could gain 1 electron to be like argon, or it could lose 7. Well, what's easier? Gain 1, lose 7? Well, gain 1 is going to be easier, and that's what chlorine would do, and it would have that octet afterwards. As we think of another example, magnesium here. Magnesium has 2 electrons in the first shell, 8 in the second, and 2 in the third. So it could gain 6 or it could lose 2. Well, what's easier? Yeah, lose 2. So as it loses those 2, we see, oh, it does have 8 in the outer shell. It's like this worked great for neon. 2 in the first, 8 in the second. Magnesium has 2 more protons than neon, so it's going to be even greater for magnesium. It's going to hold that in. Once it loses those 2, it's not going to lose any more. Again, the valence electrons where all this is happening. So, now getting into ions. Well, what are ions? Ions are elements that have gained or lost electrons. If they've gained or lost electrons, that means that they're not neutral anymore, and they have a charge. So we have 2 types of ions depending on their charge. So the first one, we have, anions are the negatively charged ions, and they must be gaining electrons to have that negative charge. And this is what the nonmetals will typically do. So nonmetals will typically gain electrons and have that negative charge. We call those anions. The other ones, it's not cations, it's cations. And cations have a positive charge. They're the ones that tend to lose electrons. And that's going to be our metals. Metals lose electrons very easily. That's why they're good conductors of electricity. So it makes a lot of sense as we think about the charges that they're going to have. Now the naming of these, it gets a little confusing when we talk about the cations, the positives, the metals. Like sodium, for instance. Sodium has a positive charge. Most likely it's going to lose 1 electron instead of gaining 7. So losing 1 is easier. But when we talk about sodium, the ion, it gets a little confusing. And that's really what people are talking about when they talk about a low sodium diet. It's not sodium, the metal that we saw blow up outside in water. It's part of table salt. Sodium chloride is table salt. And we don't see table salt blow up when we put it in water because the sodium has already lost that 1 valence electron. And now it's done losing electrons. It's not going to lose any more. It's got a super stable configuration, just like neon, with 1 more proton, though, right? So it has a positive charge. It's got a positive charge. It can stick to something with a negative charge. But the naming of it, it's a little confusing because we just use the same thing. Another example, you think about iron. You might know that you have iron in your blood. We talked about that. Well, it's not flakes of iron. It's not magnetic. You can't use a magnet to pull your blood around because it's lost those valence electrons, which is kind of a key part of its magnetism. If our blood still had iron metal in it, if you got an MRI, you would explode. Crazy. So cations, we just keep the same name. Anions, we change it. So table salt is sodium chloride. So it's not chlorine anymore, it's chloride because it gained that 1 electron and it has a negative charge. So chlorine is a gas. It'll kill you. It was used in a weapon in World War I, right? But chloride is safe. It's already gained that electron. It's not ripping electrons off of stuff. It has a negative charge, so it can bond with stuff that's positively. But we take in chloride all the time. So all of those nonmetals that gain electrons, or all the nonmetals going to gain electrons, we change the ending to "ide." So fluoride, you've probably heard of that. That's fluorine that has gained an electron, and we change the ending. So sulfide, bromide, iodide, oxide, nitride. So those are all anions that have gained electrons. So for this next part, you better grab your periodic table, because I'm going to be writing on the table and giving you some info. So first off, as we think about the alkali metals, this periodic table has the old way of putting group numbers on there, the A's and the B's, which is kind of nice, but nobody uses it anymore. So this is group 1, the alkali metals, and they all have one valence electron. So typically what happens with these is, instead of gaining 7, they're going to lose 1 electron, so they get a positive 1 charge. Holy moly, that's giant. So positive, red, that is medium. How's that? Positive 1, that's what I want. Okay, alkaline earth metals have 2 valence electrons. All of these alkaline earth metals have 2 valence electrons. So instead of gaining 6, they're all going to lose 2 electrons. So they all get a positive 2. So if you write these numbers on your periodic table, it's a nice quick way of thinking about the charges. I'm going to skip the transition metals, and we'll come back to them in a minute. So group 13, or 3A over here, they call it, they all have 3 valence electrons, so they are going to tend to lose those 3. Instead of gaining 5, they lose 3. Take the easy way out, right? Now, here's where we start to get into a problem with carbon and its family. They have 4 valence electrons. Well, you could gain 4 or you could lose 4. What's going to be easier now? Well, it depends what it bonds with. So we'll put this down as +4, -4. And the reality is that carbon is not going to make this type of bond with the ionic bonds where they have a transfer of electrons, because you need a weak element and a strong element. Somebody's going to lose electrons, somebody's going to take the electron. Carbon's not that weak that it loses electrons that easily, and it's not that strong that it can rip an electron off of something. So it makes a different type of bond, a covalent bond, which we'll talk more about in the next chapter. Next group, 15, or 5A, they say here, has 5 valence electrons. Well, it could gain 3 or it could lose 5. Well, gaining 3 would be easier, and that would make it a -3 charge. The group 16 has 6 valence electrons. It's going to be easier to gain 2. The halogens all have 7 valence electrons. They're going to gain 1. And the noble gases, right behind my picture there, is going to be 0. So you put a 0 with those because they don't have a charge. They think they're so perfect that the noble gases don't do anything. They don't want to lose or gain electrons. Now, let's talk about the transition metals. They get a little different here. Now that we know about orbital configuration, and we can talk about this D subshell that likes to be half filled or all the way filled, and it'll borrow sometimes for that to happen. When we think about iron's configuration, at the end of iron's configuration, we have the 4s2, and then we have the 3d6. So when we think about the valence electrons, really the valence electrons are the 4. The 4th shell is the outermost shell. And the iron can lose those 2. So iron can have a +2 charge. Now, like we talked about the D subshell, half-filled D is pretty stable. So what can also happen, besides losing those, is it can also lose one of these and get to that half-filled. So now it's lost a total of 3 electrons, and it can be a +3 charge. Crazy. It can have 2 different ionic states. So we'll have to do some more with this later too. Now, copper is, we look in that position, oh, it's D9. Oh, we know it's going to be 4S1 and 3D10, right? And so it can lose that 1 in the S and be a positive 1 charge. That one that it borrowed from the S is like kind of right on the edge there, and sometimes it can lose that 1 there also. So sometimes it can also be a +2. So copper can be a +1 or a +2. Now zinc has one more proton than copper, so it's got a little bit better hold, and it has that filled D subshell, which is very stable. So zinc just loses those 2 out of the S subshell. As we go down to silver, we know silver ends with the D9, so it's going to borrow from the 5S over here and be 5S1 and get a positive 1 charge. But silver is a little bit different, having more protons and more levels there. It actually holds on to that 1 that's in the D, and it only makes a positive 1 charge. So no multiple state charge for silver. Mercury, being just like zinc, has that filled D. It's going to lose 2. There is another state of mercury where it's like 2 mercuries together, so kind of working like a team. But I'm not going to get into that one with you guys. So just worry about the +2, just like zinc. And it makes sense that it's losing the 2 out of the S, and so it goes very well with that pattern. Now, let's talk about tin. Tin has its configuration with the 5S2 and then 4D10 and then 5P6. So as we think about how this is written, and like I said, we wrote it that way, but the reality of how it should be written would be 4D10 and then the 5S2. So, not, 5P2. That's right. You guys caught me on that one probably. So, when we look at tin's configuration, the outermost electrons that it can lose are these ones here from the 5P. And so it can lose those 2 and be a positive 2. Well, it can also lose those 2 from the S and have a total of 4 electrons that it's lost. So tin can be a +2 or a +4. Now right below it, same kind of deal, right? 2 in the P, 2 in the S. So lead does the same thing, +2 and +4. So those are the weird transition. There's more weird ones in the transitions, but I'm not going to make you memorize all of those. But these ones I expect you to have memorized. So it's going to take a little practice working on those, but also knowing what we know about the subshells helps, and as you think about their configurations and losing those outermost electrons. So, naming these multi-state ones, because we can't have any ambiguity in chemistry. We have to know exactly what we're talking about. So I can't say something like copper chloride, because it's like, are you talking about copper with a +1 charge? Or are you talking about copper with a +2 charge? And it matters. They're going to be different. They're going to react differently. They even look different. So with our multi-state ions, the ones that I just went over, whoops, I better move myself there. IUPAC naming system. And IUPAC is the International Union of Pure and Applied Chemistry. They're the people that get together and decide all these rules for chemistry naming stuff, and if you get to name an element after yourself or whatever too, So the system that is in place nowadays is to use Roman numerals to represent the charge of the element. So if I have copper with a +1 charge, I would write it as copper with a Roman numeral 1. So copper, let me write that first. Copper 1, right? Roman numerals. So that's how you would see it written. Now, the old school naming system, you still see things labeled with this, and I'll talk about it in class, and it might be a good bonus question on a test. So let's talk about the old school method. It uses the Latin names. Everybody loves using Latin, right? So as we think about it's a little trickier because you have to know the two states. The IUPAC with the Roman numerals, you can just, look at the Roman numeral and be like, oh, it's like chromium 3, right? It's like, oh, chromium with a positive 3 charge. I didn't know the other state of chromium, but if it's got a Roman numeral 3, that must be its charge, right? The old school, you have to know the two states, and the first one gets the us ending, and then the second one gets the ic, the IC ending. So I remember it by thinking of like us, like the team is more important than I, the individual. So us comes first before I in ic, right? So some examples. The IUPAC naming for copper with a +1 charge would be copper 1, Roman numeral 1. And I should have had a serif font here, I know, but it's what I got. And so the Latin name is cuprus. Cupric is, the second state, right there. Copper 2, positive 2 charge would be cupric. So as we think of the Latin name, cuprum is its Latin name, and so cuprus and cupric are the old way of saying the positive 1 and the positive 2 charge of copper. So iron's Latin name is ferrum. So iron 2 is the first one here of the two. It's got a +2 and a +3. So this is the ferrous, and then the iron 3 would be ferric. Tin, its Latin name is stannum. So tin 2 is the first one, and it gets stannus. And then the tin 4, and IV is for 4. They put them out of order, and that's how the Roman numerals work. V is for 5. And so that would be stannic. Now lead, everyone remembers lead's Latin name. It's plumbum, from plumber and plumbing. So lead 2 is plumbus, and lead 4 would be plumbic. So like I said, we'll see those names come up every so often. I'm going to require you to know about the IUPAC naming system with the Roman numerals. The other part is kind of the extra, but you can be super cool and throw down the Latin name, and everybody will be very impressed. So that's the start, dealing with ions and naming of everything. We're going to start putting things together and writing formulas and compounds and figure that out. But right now you have some homework that you can get busy and get to work.